We are going to show here a measurement setup to characterize the critical pulse of circuit when the circuit is driven by a large signal. The DUT we have for that is a frequency divider based on a varactor diode, and the circuit is driven by this signal generator with an input power of 10 dBm at the frequency of 670 MHz. The output of the circuit is monitored in the spectrum analyzer. For these power conditions, the circuit is not dividing yet, so we don't have any spectral line at the divided frequency here. We only have fundamental and harmonics. We are going to see now how this circuit works as we increase the input power. For instance, to 11 dBm, 12 dBm. You see that we can go up to 16 dBm and there is no frequency division. However, if we go up to 17 dBm, that's it, we have the spectral line at the divided frequency. Okay, let's go back to lower input powers, like the 10 dBm, because what we really want now is to analyze the dynamics of the circuit before the frequency division takes place. For that, what we are going to do is to characterize the reflection coefficient at the output of the circuit with this VNA. The key point of this measurement is that this reflection coefficient is going to be measured in a frequency band above the divided frequency, while at the same time the circuit is driven by a large signal at 670 MHz. So okay, let's do this measurement increasing the input power dB by dB. Like for instance, we go to 11 dBm and obtain the frequency response, 12 dBm, 13 dBm, and so on. We can observe how the frequency response changes above the divided frequency as we increase the input power. When we reach 16 dBm, the changes in the frequency response are huge because we are close to the bifurcation. Now, we take all these frequency responses, we put them on a file, and we export it to a stand tool in IVCAD from UNCAD Engineering. And that's it. We are in a stand tool now, and the first thing we are going to do is to open the file that we have just exported, which is this one. We open it, and what we want to do is to perform a pole zero identification of all these frequency responses. So for that, what we are going to do is to select an order 7 for the transfer function. And you will see that the identification process is a very fast process. We just click here and identify, and that's it, the identification is done. We can see the results for all the frequency responses, like that. And for instance, we can plot their poles on a pole zero map. And that's what we get. We see that we have two pairs of complex conjugate poles with negative real part that are about the divided frequency. And what we want to see is we can see this evolution in more detail, making a zoom like that. And this is the pole evolution that we get versus input power. We can see this step by step, starting from 10 dBm. These are the two poles that we get from 10 dBm, and then going up to 11, 12, and so on. We see how these two poles move to the right, the stability margin is decreasing, and the two poles tend to collapse. And once they collide, one pole keeps moving to the right, which is this one, and the other one moves to the left. The thing is that if we go to 16 dBm, identification starts to fail a little bit, and you can see, for instance, this location of this pole here. This is, to understand this, we have to go back to the measurement setup. We are back in the measurement setup. So now, if we center the spectra at the divided frequency, and we select a narrow resolution bandwidth, we can see that for 16 dBm, we see a noise bump in the spectra at the divided frequency. This is a noisy precursor, and it's very typical before a bifurcation takes place, and we see it many times in the lab before an oscillation happens. Actually, this is the reason why the pulse identification starts to fail for 16 dBm. Now, if I go to 17 dBm, the oscillation shows up.